Hello, welcome to my YouTube channel. We continue with solve problems, and today we're going to talk about solve problem 3. And the question reads: calculate the binding energy of the Roman 1 last proton and Roman 2 last neutron. And we're going to do it for the nitrogen 14 nucleus. And after doing it, we realize that the values are different. So we're going to explain why the values are different. And we have as data the masses of nitrogen 14, nitrogen 13, and carbon 13 atoms. Please, they are masses of atoms, not masses of nuclei. And we also have the mass of proton, the mass of an electron, as well as the mass of a neutron given to us. Let's look at the physics principle that is guiding this problem. Generally speaking, the energy that is needed to separate a particle from the nucleus is known as separation energy. And this energy depends on the type of nucleus we are considering and whether the particle is a proton or a neutron. If it is a proton, then the separation energy is called the binding energy of the last proton. And if the particle is a neutron, the separation energy is called the binding energy of the last neutron. Binding energy of the last proton. It is the energy that is needed to remove a single proton from a nucleus. And if we do that for nitrogen 14, we end up with carbon 13. You can check the equation to see that the mass and atomic numbers on both sides are the same. Now, binding energy there represents the mass defect. So it is clear that the mass of nitrogen 14 is less than the masses of carbon 13 and the proton. So to get the mass defect, we will subtract the mass of nitrogen 14 from the sum of the masses of carbon 13 and the proton, while also making sure to check out the mass of the extra electron in nitrogen 14, since we are giving the masses of the atoms, not the masses of the nuclei. You can clearly see that nitrogen 14 has one extra electron than carbon 13. And if we do that, we're going to have 0.0081 U. And we know that 1 U is 931.5 mega electron volts. So our binding energy will simply be 0.0081 times 931.5, and that gives us this value 7.55 mega electron volt as the binding energy of the last proton of nitrogen 14 nucleus. Similarly, the binding energy of the last neutron is the energy needed to separate a single neutron from a nucleus. So in this case, if we supply energy to a nucleus to remove a neutron, we are not going to have a different element because the proton is not affected. So we still have a neutron, just that the mass number will change. And we have now a neutron. And the mass defect is given as shown. And that gives us a value of 0.011 U. And similarly, we have the binding energy for the last proton as 10.55 mega electron volt.